Today I'm going to be doing a practice problem, and it's related to the Heisenberg uncertainty principle. Now, what that is I'll write out the equation for it right here. Delta x times delta p is greater than or equal to h bar over 2. Now, these delta x's and delta p's, what do those really mean? They're just uncertainty and position and momentum, respectively. And what that uncertainty means is it's basically like when you're doing an experiment and you get a bunch of results and you have a margin of error for those results. Because the thing with quantum mechanics compared to classical physics is that it's a lot more statistical and it's very probabilistic. And so things like margins of error and uncertainty are going to be really, really relevant when you're doing it. And the practice problem goes like this. You have an electron and you measure where it's at. And you figure out that your electron is within some volume and your uncertainty of where it is within 1 angstrom, which is 10 to the negative 10 meters. It's a very, very, very small volume. You've pinpointed where this electron is with really great certainty. But because of that, you're not really going to know that much about its momentum. Now, what is momentum? Well, it is mass times velocity. And so because you don't know very much about your position, not your position, you don't know very much about your momentum, you're not going to know very much about your velocity. And what this practice problem was asking is, what is your uncertainty for velocity? Now, you multiply these out. And I'm going to change this delta p here into an m delta v because p equals mv. And, I set this greater than or equal to h bar over 2. Next, I'm going to do a little bit of rearranging. So I'm going to erase the uncertainty principle so I just have a little bit more room. And I'm going to move everything to the other side. And it's going to look like this. I'm going to divide by m and delta x on both sides, and I'm going to get that delta v is greater than or equal to h bar over 2m delta x. And here I'll erase this on the bottom. So now I just have this equation. This is our uncertainty in velocity. Now, what is this going to tell us? It's going to tell us, well, we know where this position is within an angstrom. And our velocity, because we know where that position is so well, we're not really going to know what our velocity is. But what we're trying to figure out with this question is by how much do we not know what our velocity is? So I have my constants written down here. We're talking about an electron here. And so I have the mass of an electron here, and Planck's constant, so I can calculate the constant in the uncertainty principle. And we're just going to plug all this in and figure out what this is. So h bar is h over 2 pi. And so we can simplify this. We could say delta v is greater than or equal to h over 4 pi m delta x. And we have all our values for this already. M is the mass of our electron, and delta x is our 1 angstrom. And now I need to plug this into my calculator to figure out what this value is. So we have h, which is 6.626 times 10 to the negative 34. And we're going to divide that by all of this. 4 times pi times 9.109 times 10 to the negative 31 times our delta x, which is 1 angstrom, which is 10 to the negative 10. And we'll get our answer. And it is a very, very, very big value. It is, I'll write it down here on the board. Let me get rid of this. And I'll actually get rid of this too. Write our answer big and grand here. Our uncertainty in velocity has to be at least 578,856 meters per second. That is really big. That means, what does this mean really? It means that we don't know what the velocity is, like, at all. I mean, this is a really big value. It could be within a whole range of velocities ranging to thousands of meters per second, hundreds of thousands of meters per second. I mean, we don't know what the velocity is, right? And that kind of illustrates, I think, really the significance of this equation right here, Heisenberg's uncertainty principle. So you have your delta x delta p greater than or equal to h bar over 2, start 2 pi. And what it's really saying is that, and I'm going to restate this, I've already talked about this, but it's really important when you're doing quantum physics. And it's that if you know where your position is within a really small amount, you're really precise and accurate with your position here, you don't know what your momentum is. I mean, like, if your margin of error for momentum is so high that you don't know what it is, right? And that's really what this is saying. It's saying that in quantum physics, when you're working with your really small particles and your microscopic systems, it's saying that you can't know these two things, position and momentum, at the same time. You know, there's always going to be uncertainty in one or the other, and that's really what makes quantum mechanics so weird and hard to grasp. But yeah, that's what this practice problem illustrates. It's from this book here, this Modern Physics Workbook. It's a pretty good one. It's by Chris McMullen. And yeah, it just has a lot of these problems, but that's where I learned this. It's a really fun practice problem. Anyways, thanks for watching.